Hi, should we start? I think you're on time.
Yeah, quite a good numbers.
Yeah, people have joined, so I think we'll start. Good morning, good afternoon, good evening to all the participants who have registered and logged in from various parts of the globe. Hope you can see the screen and I'm audible to all of you. Am I audible?
Yeah, perfect.
Okay, so welcome to all the panel members. Good to see Shekhar and Gils also joining us. So we are going to have a good session today. Welcome to all of you on this Plastics Flame Retardancy Learning Series number 4, Testing of Flame Retardant Characteristics, Part 2. We've already completed the Part 1. Jointly Formulated Polymers Limited, India and Eurostar Engineering Plastics plants are presenting this. And this is basically for all the practicing professionals, whether in the electrical electronics industry, in the automotive industry. I think today both Krishnamurthy and Alexi will also be discussing about railways and some of the standards which are applicable for the railways. And this is mainly for those people who are involved in design, selection, processing, testing, application of various engineering flame retardant thermoplastics. So I am Rashmi Bhardwaj, working in Formulated Polymers Limited as a Vice President Development. The webinar is of 45 minutes, 40 minutes for presentation and 5 minutes for QA. I'm a moderator for the session. So please request you to post the questions in the question and answer box below and not in the chat box. This is the series which we are presenting. These are the flyers which have been circulated to all. We have completed 3 series, that is series 1, history, need and ISO classification of flame retardant chemistry. Series 2, where we discussed on flame retardant mechanism and selection criteria. Series 3, which was on testing of flame retardant characteristics, where we covered up the UL 94 and the glow wire tests. Presently, we are doing the series 4. Subsequently, we have planned series 5, which is on standards, how to read the UL and the VDE standards. Then subsequently, we are doing a few more on processing, design perspectives, environmental impact, and of course, some of our specialty products like the cross-linked polymers. So we would appreciate if some of the industry professionals come forward and present some of the series. Some of the industry professionals have already agreed, so we are looking forward to their presentations. This is basically a learning program, and it's a revision for some and it's learning for some others. So since Eurostar Europe and Formulated Polymers Limited specialize in compounds of engineering polymers, most of the examples will be based upon polyamides, acrylonitrile, butadiene styrene, polypropylene, polycarbonates. So now about the speakers, we have Mr. Krishnamurthy, GM Operations, Formulated Polymers Limited. He's a master's in science and with the 29 plus years of experience in various fields, including design, development, production, quality assurance. He has almost 15 years of experience where he is linked directly to development of 300 plus new products in the electrical and electronic segment and the automotive segment. Krishnamurthy will be discussing LOI and the smoke density tests. Another speaker, Alexi Chopin, he is technology manager, Eurostar Engineering Plastics. Alexi has a master's engineering degree in plastics engineering from ITech Lyon. He's 25 years plus experience in formulation, compounding, and application development. He's a co-applicant for many patents in FR engineering plastic compounds, including cross-linked polyamide. He's basically a very good subject specialist for low voltage and medium voltage controls. And he will be discussing on CTI, hot wire ignition, HAI, RTI tests in detail. Just to do a quick recap of the series which we have already carried out. The first series was basically on history, where we discussed fire accidents, what is the reason why we started using flame retardants, the ISO classification as per ISO 1043, which was discussed in detail. We have the YouTube link for this series, and anyone who missed out on this series can definitely go on the link and review the series. Then we had series 2, where we discussed the flame retardant mechanism, various endothermic processes, the radical quenching, the thermal shielding, which is involved, as well as trend towards more environmental friendly FR systems, and the legislations with respect to the changes as far as environmental concerns are concerned. We discussed halogenated nitrogen, organic, inorganic phosphorus compounds. We also discussed the metal oxides, hydroxide salts, boron zinc compounds, silica compounds, and some specialties. Here also the link is available for all those who missed out. This was our previous series 3, where we discussed in detail regarding the flammability testing. UL 94 discussed in detail with examples and actual applications. Glow wire flammability test, also we had live presentations where we showed how the entire test is carried out. I think now I'll hand it over to Krishnamurthy. He will be discussing on the tests. So I'll ask, I'm stopping sharing. Krishnamurthy, you're asked to join.
Thank you, Dr. Roshmi. Welcome all participants for today's session. Hope I am audible.
Yeah, we can hear you.
Okay. Slide shows list of flammability tests for plastics. This series of tests can help to determine how products behave when exposed to flame. Earlier in series 3, we discussed UL 94 and glow wire flammability test. Test standards, equipments required, test procedures, acceptance criteria, and areas of application discussed in detail. In today's session, we are going to learn another flammability tests like LOI, smoke density, CTI, HAI, RTI, etc. We start with limit oxidation index. LOI test follows ASTM D2843. Limit oxidation index is standard test method to measure the amount of oxidation requires from atmosphere to burn. 3 important things accelerate the fire glow. First one, fire source. Second, fuel or burning material. Third one is oxidation from atmosphere. Pure air in atmosphere contains 21% of oxidation in normal conditions. Material less than 21% of LOI value are easily burned in atmosphere. It absorbs more oxidation from outside and added to flame as a fuel. Material more than 21% LOI value burn slowly. There is an history behind this test. Before successful 1968 moon mission, NASA faced one tragedy. In the year 1966, 3 American astronauts burned to death in a space capsule on top of first Apollo rocket during test. What happened now? Instead of air, the space capsule contained high percentage of oxygen, maybe planned for easy breathing. Apparently, a spark from the electrical equipment ignited the plastic insulation cabling, and the resulting flash fire caused the death of astronauts. After this accident, NASA studied the importance of oxygen percentage level in the air and fixed specification as less than 10% in space shuttles. For LOI test, we request glass chamber or chimney. The dimensions of gas column, height will be 450 to 500 mm, and inner dia requires 75 to 100 mm. Test specimen can be any type, molding, cut piece, sheets, etc. 80 mm length, 10 mm width, 4 mm thickness specimen used in this test. Here pure air used as gas, 98% pure dry air with 20.9% oxygen nitrogen mixture flows inside the chimney as a gas. All ASTM IEC standards require specimen conditioning before test. Test specimen conditions for 40 hours at desiccators 23-50% RH. Glass beads placed under specimen holders to avoid air leaks. Now we see the LOI values of materials. Test procedure of LOI is simple and almost similar to VB test. Here also specimen clamped vertically in the test stand. Using our similar products experience, initial oxygen percentage to be set. Specimen ignite using used type burner from the top of column. Ignition time 15 seconds at top of specimen. Remove flame and allow specimen to burn for 3 minutes or 50 mm length. Record rate of burning of specimen as in the case of horizontal burning. If specimen not burning required time or length and self-extinguish, we need to increase the oxygen level in the air mixture and repeat the test with fresh specimen. Test continues till LOI value determined. Now move on to LOI application part. Limit oxygen index is scientific and technical measuring method of flammability. This test helps as QC tool for designers in the field of resin product manufacturers. Flammability of any material influenced by several factors such as ease of ignition, flame spread, fire endurance, rate of heat release, toxic gas smoke density. LOI plays role in determines flame spread. It helps designers in the area of personal protective equipment, electric and electronics, textiles, mass transportation sectors, railways and aircraft, then automotives. Slide shows the role of limit oxygen index in personal protective equipments. Fabrics are made from plastics. Many fabric contain 16% of plastics using polymers, polyester, nylon, acrylic. LOI test helps to design fabrics for firefighters and emergency frontline workers. PPE are classified as civilian PPE, military PPE. It also classifies as level A, level B and level C as shown in the slide. Level A requires full protection for respiratory, skin and eye. Normally, it requires the person who working in unknown area, that is in hazardous area, maybe LOI value of less than 20%. So this type of person requires nylon flame retardant fabric with high LOI value greater than 25%. In level B category, requires eye protection for respiratory and minimum level for skin and eye. Those persons normally working at greater than 20% LOI area requires polyester type slow burning fabrics, contains LOI 20 to 25. In medium category level C, mostly for fire receivers or second line workers. For level C persons, normal burning fabric like cotton will serve purpose fully. Then now we move on to LOI application cable industries. Electric wiring is part of the fire protection system. Cable firing is major cause for any electrical fire. Plastics with high LOI values like nylon, PVC, PE are normally used for cable sheathing. Plastic coated cables does not burn in normal air, but in high oxygen content and overload environment, cables behave differently. Addition of FR additive helps to improve LOI values considerably. Fire resistant classifications of cable given in below tables. It shows fire resistance duration in minutes, that it classifies as E30, E60 and E90, which means it resists fire in required minutes. For E30, it resists up to 30 minutes in worst environment. In right side photo, we see top photo, cables made up of PVC with highest limit oxygen index values greater than 35. It shows low fire and smoke generation and very low smoke, almost nil smoke generation observed. In the middle, cable made up of nylon of medium LOI values greater than 30. Fire and smoke generations are little and it is slightly visible. And bottom one cable made from plain HDP of LOI less than 25. It exhibits fire and generate more smoke, almost starts burning. This experiment shows the importance of LOI values in cable industries. In my last session of this FR series, we discussed in details about UL flammability test. Slide shows the relationship between LOI versus UL94. Non-FR material meets LOI values below 20%. The slide graph shows LOI values increase with increase of burning rating. V2 meets LOI of 22 and V1 will fall to the range of 25. I rating V0 will be close to 30 LOI value. Then for highest rating 5V and 5VB matches LOI is greater than 35. Flame retardant compounds having highest values of LOI. And we move on to next important flammability test, smoke density. Smoke inhalation is a major cause of death for victims for fires. The biggest health threat for smoke is from fine particles. These microscopic particles can penetrate deep into lungs and cause a range of health problems. 5% of material used in buildings release high amount of flames during burning. Two standards given on slide are widely used to measure smoke density. ASTM D2843 measuring the density of smoke from the burning or decomposition of plastics. The next one, ASTM D662 covers determination of specific optical density of smoke generated by solid materials. This standard mainly referred for materials in railway, aircraft and other public transportations. ASTM D2843 standard measuring smoke density for plastics. We see smoke chamber design in the slide. It made from aluminum with high heat resistant glass doors. It has an ignition system using propane gas, and specimen order will be there inside. Light source of compact filament microscopic lamp. Box on left side of chamber contains photometer. As like other test, timer device also important tool with easy reset option. Specimen needs to be conditioned before testing. Then test procedure, first turn on photocell lamp, switch on gas, ignite burner and set pressure at 40 psi. Calibrate the photocell at zero absorption. Then ignite the specimen using burner. Specimen should be ignited from the bottom. Observe the light observation at 50 seconds for 4 minutes duration. Test should be repeated with 3 sets of specimens. Maximum smoke density, total smoke generation can be calculated by drawing a slope between time and light observations. The next one, ASTM E662. This method used to measure optical smoke density arises from burning solid materials. widely using in transportation sectors like aircraft, railways, etc. Test equipments are similar that of previous one. Here specimen ignited using radiant flux, smoke density dm and rate of smoke density ds to be measured. Specification of rate of smoke density of certain material used in railways given in slide. For transport sector requires ds of less than 100 mm at 90 seconds, and in certain cases it required less than 200 at 240 seconds. The slide shows the amount of smoke released by various polymers when contact with fire source. From chart at top, TSP refers total smoke production and SPR tells peak smoke production. HAPS and ABS shows high level of TSP and SPR. So these type of polymers not in first choice in passenger compartments. Nylon, PP, polyethylene has low rate of TSP and SPR, preferred one for auto industries. In second graph, we see generation of carbon monoxide by various polymers when burning. Carbon monoxide is narcotic gas and one of the major cause for fire-related fatalities. Chart again shows polyamide, PP, PE emit less amount compared to HAPS, PC, etc. Slide shows the list of plastic parts used in all types of mass transportation sector. In aircraft, ceiling and wall panels, partitions are made up of plastics. In railways, seat frames, mattresses frames, foot trays. Then of course in passenger cars, seats, gears are all made from plastics. Smoke density test needs to be tested in all go-karts. DS, TSP, SPR, carbon monoxide values tested and confirmed with the design specifications. Low toxic gas generation polymers like nylon, PC, PP, PE are commonly used for above applications. Flame retardant compounds are also high demand for above applications. Then we move on to European Railway Standard for fire safety. It has EN 45545. It introduced as mandatory requirements for full Europe. It aims to protect passengers and rail personnel from onboard fire accidents in railways. In these standards, fire performance tests to all railway components like flooring, seats, cables, wire accessories, wire ducts, etc. LOI, smoke density and smoke. There are three hazardous levels classified as HL1, HL2 and HL3. HL1 being the lowest level and HL3 highest level. Products are classified according to 26 requirements, R1 to R26, depending upon where material used. Example, R1 ceiling and walls and window frames. Then for R26, small electronic parts. The above classification made based on how many kilometers rail travels in tunnels, whether it is automatic one or whether it has a sleeping coach. So a lot of parameters are taken into consideration before drawing the specifications. Table shows R22 requirement standards for high hazardous level. HL3, LOI and smoke density and DS values are 32 and 150. For low hazardous level HL1, it varies to 28 and 600. So this slide shows various ranges of tar flame grades of high performance polyamide compounds to meet stringent EN 44545 requirements. It covers ranges from unfilled to glass fiber filled in both PA66 and PA6 polymers. In neat resin category, we have Star Flame 1P100ZE, which meet HL3 requirements and V0 at 0.8 mm. Then also in glass field ranges 35 and 25% meets V0 0.8 mm. Then for HL3 requirements, cross-linkable polyamide 6,6 with 30% glass field ranges are available. That's all from my side. Thanks for your patience. Hand over to Roshni for next session.
Yeah, thank you, Krishnamurthy. Thank you very much for explaining in detail the limiting oxygen index, especially going into details on the ASTM standard D22863, which measures the minimum level of oxygen in atmosphere and in which any material can sustain flame for thermoplastics. Higher the LOI, the less likelihood of combustion. And also we understood ASTM standard D2843 and E662. What is the difference between the two standards? Thanks very much, Krishnamurthy. I'd request Alexei to share his screen and discuss on the high ampere arc ignition, comparative tracking index, high voltage arc tracking rate, as well as the RTI, that's the relative thermal index, as per the UL 746B. Over to you, Alexei.
Okay, I hope you can see my screen.
Yes, we can.
Oh, it works perfectly. Then we are lucky today. Okay, so today we'll go through a few measurements that are of vital importance for E&E because they are mentioned in the UL 746C, which is the basic for selection of material. So we will start with a comparative tracking index, so-called CTI. So CTI is a test that simulates the case that a current develops due to a surface contamination of a plastics insulator between two conductors. So basically, what is tracking? Tracking is a current flowing on the surface of an insulator between two electrodes caused either through pollution or degradation of the insulator. So tracking resistance is the ability of the insulator to prevent such current. So what is the layout? The layout is quite simple. You have here a specimen, which is a UL standard specimen. You have two electrodes, and you have a system to release droplets. The liquid which goes, that composes these droplets are not pure water, because the test is to simulate contamination. So the water is loaded with 0.1% of ammonium chloride, which is an electronic pollutant. Then these droplets falls between those two electrodes every 30 seconds. So every 30 seconds you have a drop which is going down, and then of course there is a current applied to these electrodes, and the pollution tends to make contamination on the surface, and if the current is high enough, then there is a formation of a conductive carboning spark between the electrode, and to a standardized level of current. If a standard level of current is reached, then the measure is done. So the test specimen is standard. The test voltage is between 100 and 600 volts. It cannot be chosen by chance. There are steps. So basically it's 175, 250, 300, 375, 500, and 600 volts, which are the most common. The EEC solution can be checked by conductivity. The drop volume has to be calibrated, and this is very, very tough point of this measurement. And the failure criteria, meaning that measurement stops if there is a current more than 0.5 amperes for more than 2 seconds, or if the material burns. And the performance is expressed as the number of drops that the material survived before arcing. So this is true, but there is a tendency more and more, and your customer, as a customer, you will see that, is to take into account also the flame. There is a criteria in the standard, which is not, let's say, a failure criteria, but an observation is the creation of a flame and the time that the flame occurs. So a material which is not good for E&E has a CTI less than 100 volts. Of course, in our domestic application, we are 220 or 110, depending on the countries. So a material that is very suitable for electrical application has to be above 400 volts. And in a UL standard, you will see a PLC, performance level category, and surprisingly, it's the reverse side, meaning a material with a high CTI, 600 volt, is a very good one. A material with a low PLC, 0, is a very good one. So most of the time, for E&E application, you need to have a PLC 0.1, or in certain cases, if you are not too close to VR, to 2. There is a lot to say on this testing. Electrodes are in platinum, and it's very important because sometimes, for cost reason, people are using, and the way we do sometimes, electrode in brass, but you can have interaction and creation of conductive ions. For example, for some halogen-free material, if you have brass electrode, then you can create a kind of conductive copper-phosphor system that makes the material conductive. So it's very important if you compare that. CTI of material. You have very good material but have very poor CTI. And for example, PPS is a very high thermal material, but you never see close to the arc because it's very poor in CTI. Same thing, you've never seen MCB closure for a contactor or a circuit breaker or in polycarbonate, because it's a good material, but it's very bad for arcing. Then you see in this chart that material that behaves very well is polyamide 6 and 6,6. And it's not a chance that many material for electrical and electronic application are made for more than 30 years in nylon 6 or polyamide 6 or 6,6, because inherently it has a very good resistance to the arc. On the small picture, you will see the behavior of a non-halogenated flame retardant. Typically, you see that there is a few generations of flames. It's very small, and very often non-halogenated material have very nice CTI, sometimes $600 and above. For halogenated FR, you have most of the time creation of a conductive part, and the CTI is more limited, around 300, 400 volts. So another test which is of prime importance for electrical application, and you will see that also you will find in the UL 74-6C, is the hot wire ignition. The objective in this case is to judge the ease of ignition of a plastic part which is in contact with a heat source, but not an open flame. The test simulates the case that a plastic part is in contact with an overheated electrical wire. This is what you see here. So basically, you round up a wire onto a UL bars, like KK described. You apply a current, and then you measure the time to collapse. So the collapse is measured or by a flaming, or if the material survives well, sometimes you have a material which is melting and vanishing from the wires. And the time has to be stopped when there is no more material to be burned. Then too, you are measuring the time. So you see, for example, a material which takes fire in less than 5 seconds has a very low PLC, a very high PLC, which is not material suitable for the application. But we have material that can withstand above 2 minutes, meaning that will have a PLC 0. In our range, we have many materials in the range of PLC 0, 1, and 2. And in some cases, it's really of vital importance, because if you have a material which is of PLC of 1 or 0 or 1, you will see maybe in the next presentation, you can choose material that has still V2 or even HB in performance. Then another test is the high arc ignition. Then it's a bit different. The test, in fact, is simulate the situation that an arc occurs between 2 electrodes under a low voltage but a high current. For example, 2 connectors spin on a plug. The arc is created on the resin of a plastic, on surface of resin. So you have a fixed electrode, which is in copper, a movable electrode, which is in stainless steel, under normal current, and you are moving back and forth this electrode 40 times per minute to create an arc. And then you will have to see the time to ignition. And the same thing as previously, it is rated as or by a number of arc, or by a PLC. So the same thing, of course, if the material withstands the arc for a long period of time, a great number of arc, then a PLC is 0, meaning that the material is well suitable for electrical application. These are quite simple tests, but most of the time they are run directly at UL, because it's not an apparatus that you find in every laboratory, of course. Huh? The arc resistance. Arc resistance is even another test. It's very similar on the principle as the CTI, but in this case, the voltage is very high. So this method is intended to differentiate in a preliminary fashion among similar material with respect to their resistance to the action of a high voltage, low current arc close to the surface of an insulation, tending to form a conductive path, causing the material to become conductive. So in this time, electrode is not moving, is fixed, but you have a high voltage that is applied to the system, and you are measuring the time to arcing. So it's expressed in seconds, meaning that you are the voltage is varying automatically, and you're measuring the time to formation of a conductive path. And depending on the results, of course, you have different performance level. So if the time is below 1 minute, then the material is really not suitable for E&E application. And it's above many minutes, then you can really use it for applications in E&E. So this was, let's say, the most of what you will call the short-term properties at UL. So you will see there is, in next presentation, I think there is a table that summarizes that. And depending on the different level, you have the right or not the right to use the material for an electrical application if you have to apply to UL standard. Another measurement which is very, very important for the application is the RTI, Relative Thermal Index. Because when people ask the question, what is the thermal resistance of a material, most of people are thinking about HDT. HDT is the heat distortion temperature. It's listed on the datasheet. It's a very easily available material, but the problem is that HDT is measuring only the short-term properties. It do not indicate the temperature at which a material can resist for a very long period of time. But of course, when someone designs a part, it does not have to survive just during the homologation phases, but it has to, for E&E application, almost for 20 years. So there is a way to measure this almost continuous in-use temperature, and it's done by UL, and it is called the Relative Thermal Index. So it's measured according to standards, of course, and Relative Thermal Index, temperature index, sorry, is the maximum temperature service that the material can survive, let's say, for an infinite period of time. Of course, nobody can simulate an infinite period of time, so UL has a method to test with time equivalence temperature, where we can forecast for 60,000 hours. So 60,000 hours means 7 years. So how it is done? It is done in ovens. So we are submitting specimen, or we are aging specimen in ovens, and at different temperature. And from time to time, specimens are removed from this oven, and they are tested mechanically or electrically. This is what we see in this curve. So just to explain, we are measuring, for example, the properties versus time. The yellow curve is, for example, let's imagine it has 200 degrees C in an oven. You will see a properties. It can be an impact properties, a tensile properties, and of course, during time, material is aging and properties is going down. An important point is what they call the half-lifetime period, meaning that the properties is cut into two, 50%, a retention of 50%. So you have, for example, T1 is the time for 50% mechanical properties retention at 100 degrees C, 200. Then you are increasing the temperature of 20 to 30 degrees. Do the same exercise, you have an average temperature for the half of life and a third temperature. Then you plot on this chart the time temperature relation. So, and you draw a curve of half of life properties. So you have a regression curve, and you say at any temperature, the half of life temperature, and it extrapolated to 60,000 hours at UL, and it's the value you can find on the yellow card. Some customers are also requesting the thermal index at 5,000 or 20,000 hours, but can be extrapolated from this curve. So it's a very important data. So you have to, of course, it's also maybe a bit questionable because there is no absolute properties. And when you do a test, you always do in comparison with a standard, with a competitive material. So what do we determine? Basically, this is what you will see on the yellow card, 3 different properties. The electrical RTI, which is, in simplifying, let's say, the continuous in use temperature for electrical properties. So it's measured most of the time on dielectric strength. The RTI with impact, it's measured most of the time on impact bars, Sharpie or ISO. And you have the mechanical strength without impact, which is most of the time measured on the tensile bars. So you have 3 important properties that can simulate the continuous in use maximum temperature for this material. And then maybe a warning from my side, it does not mean that you can use this material at this temperature, because of course the material will lose 50% of this property after a certain period of time, of 7 years, and of course it gives no idea about the surface of material. Material will be oxidized and color carbon black. Nonetheless, it will withstand, let's say, according to the standard. So FPL and Eurostar are really a very nice range of products, and it's a very nice asset, because you have to know that this test lasts for about 18 months, and it's really a big investment. A yellow card with a full RTI costs $100,000. And we are in this market for so many years that we have very documented material, and we have even material that has RTI above 150 degrees C. And this is quite exceptional, let's say. I have to go fast because I see I'm almost late. But you see on the material properties for standard material, you see the RTI ranging from different polymers. And you see that nylons, polyamide 6 and polyamide 6s have already a good RTI that can be boosted with glass fiber and with stabilizer. And in our cases, we have materials with RTI above 150 degrees C. So this is really a strength. Where does it applies mainly for power distribution system, for feeders, switches, protective equipment, circuit breaker, more and more in transportation, for battery, housing, cable, power carrying components, and within time, it will really come for electrical vehicles. So just this table that we put on every presentation, because we think it's really relevant to see that there is no perfect material. If you see a material with a good RTI, then you have nice things, but it's always a matter of compromise. But we have really a full range within our combined range of FPL and Eurostar, fitting most of the needs of a material. Okay, I think I'm very sorry. I think I've been too long as usual. So I give the voice back to Rashmi.
Thank you very much, Alexei, for explaining in detail the testing procedure and correlating it with the application requirements. Comparative tracking index you discussed in quite detail, and we found it very interesting. I actually didn't want to stop you because the way you explained it is very wonderful and very informative. So what you have discussed is that live parts, current carrying parts must be resistant to tracking. So I'll just share my screen. Just a minute.
Yeah, I think you can ask. It's only a question.
Yeah, I can ask the questions because as it is, we are running short on time. So we have a few questions lined up. Since we are short on time, if we miss any questions, we'd request you, we'll be sending replies by mail and we'll definitely be responding back on those questions. The first one which has come to us is, what is the reason of smoke in flame retardant compounds, especially engineering plastics? How to control and reduce the smoke? This is K. Manivanan from DC Engineers, Mumbai. So this is a question to all the panel members.
I don't know, KK, if you want to answer, but smoke is related to many things. For instance, the first thing is the polymer, because polymer is fuel. So when you are burning a polymer, you are generating some fumes. So at the end, it will fume for sure. But of course, we have an action on fumes, because by selecting the right flame retardant, you can really control the level of fumes. Meaning, for example, it's well known that brominated flame retardant tends to fumes dark and heavy, because sometimes they are composed of brominated polystyrene. And if you have ever burned polystyrene, you see that it generates a lot of dark fumes. So we can control a lot of the fumes. And fumes can be controlled many ways by selecting. And what to say? I don't know. We can really control fumes on plastics, yes.
Yeah, Krishnamurthy, you want to add something on this? We can't hear you. We can't hear you.
Okay, sorry.
Yeah, now it's
I'm
better.
in unmute mode. Okay, now I unmuted. Yeah, smoke is directly related to the FR compounds. Normally, brominated FR chemistry will have a more smoke compared to chlorinated. And it also directly responsible for limit oxygen index, as is seen in our previous slides. If it has a high LOI, it has a low smoke normally.
Okay, thanks, Krishnamurthy. Thanks, Alexi. There's another question. Which are the compounds for high CTI values, especially which can be used for live parts?
And halogenated FR components normally will have a low CTI values. For high CTI, normally we have to go with phosphorus and nitrogen based. Then of course, the MCA chemistry will have a medium CTI close to 450. So for high, normally we have to go with phosphorus and nitrogen based.
There is another question which is coming from Ajay Singh from National Electronics, Noida. He's asking polymers, which polymers are used for fire protection, and how do you correlate this with the various tests?
Yeah, there is some correlations between test. Actually, for limit oxygen index and the UL94 flammability test, we have some correlations. For a high rating, V0 will have a LOI value of more than 30. Then for V1, V2 classification, it has some reference to LOI values. So there is some correlation between flame. Yes.
I think, thank you very much, everyone. We are running short on time, so we shall respond to rest of the questions by email. We have scheduled the next series, which is the series 5. It's tentatively scheduled for 15th October, where we'll discuss how to read the UL and the VDE standards. We are still in the process of finalizing the speakers, so definitely we'll be coming back to you. And we'll be also, this date is tentative, so we'll be finalizing it. Request your feedback, and in case you have any queries or you'd like to have some more information, please feel free. And you can visit our website also, the formulatedpolymers.com and the Eurostar-EP.com. Finally, I thank everyone for joining in, and we appreciate your support and hope that you have gained from this webinar. Once again, thanking all the participants and also the panelists, and also a support and cooperation from our IT team, Venkatesh, and from Shobna in R&D for making this series a success. Thank you very much, everyone.
Thank you very much. Good luck. It was
Yeah,
nice.
thank you.
Bye.
Yeah, bye.